Perfect. So welcome back. We will now start the afternoon session of the conference. Um, our first speaker is Yaithd Olivas from UNAM. As usual, if you have any questions, you can either just unmute yourselves and politely interrupt the speaker, or you can just raise your hand and I'll interrupt the speaker on your behalf. So Yaithd, you have 30 minutes and then we will move on to 10 minutes of questions. So take it away.
Okay, thank you. Can you hear me?
We can hear you just fine, yes.
Okay. Okay, first of all, I would like to thank to the organizers for giving me the opportunity to present my work here. The title of my talk is this one, Holographic Integral Geometry with Time Dependence. This work was done in collaboration with Bartek and CE1 from the Institute of Advanced Studies in Beijing. So let's start. As we all know here, the general statement of the ADS-CFT correspondence says that any conformal field theory on this space-time is totally equivalent to a theory of quantum gravity in asymptotically ADS space-time. Of course, there is a dictionary that allows us to translate physical observables from one side to the other. And one observable that is of interest for us in the rest of the talk involves the computation of the entanglement entropy. Essentially, the entanglement entropy is going to be equal to the area of some extremal surface. And such an extremal surface you can see in this figure for a specific case in a specific set of coordinates. So for the rest of the talk, I will focus only on the ADS3-CFT2 correspondence. Here, the extremal surfaces that compute entanglement entropies are space-like geodesics. And we can use a combination of entanglement entropies associated to different spatial regions, in this case are intervals, to obtain a different prescription to compute the length of a closed space-like curve in the bulk. Essentially, we have that some information theory quantity that we are going to call, we know as differential entropy, is going to be equal to the length of a closed curve. I will elaborate more on that later, but let me just put a drawing of what is happening in this case. So I don't have to say that entanglement plays a key role in understanding the bulk geometry. So therefore, we need a formalism in which entanglement is treated as a central object. And using as a starting point the differential entropy formula, it was possible in the static case to establish a formalism called integral geometry by these people. The main result of this formalism is that essentially we can compute the length of a closed curve in the bulk as an integral over the geodesics that intersect this curve. Of course, we would like to generalize this prescription in the case where this gamma can have a non-trivial time dependency. But if you try to extrapolate this result naively, you simply would see that it doesn't work. So the main result of this talk will be to address this problem in the time-dependent case. So let me review some basic facts about ADS3. As we all know here, the identity space is a maximal symmetric spacetime with constant negative curvature. And we can identify this space as a submanifold of higher dimensional Minkowski space. The explicit form of the embedding in this higher dimensional space is given by this equation. And we can see from this notation that the isometry group is SO2,2. We can use a specific set of coordinates that are called global coordinates, and we can write down the line element in the following form. So let me now introduce the concept of entanglement entropy. This concept can be defined in any quantum system that admits a separation of its degrees of freedom into components. That is, the total Hilbert space can be written as a tensor product of a Hilbert space that describes the degrees of freedom of the first part and a Hilbert space that describes the degrees of freedom of the complement. In a quantum field theory, the natural way to separate these two components is by choosing a specific spatial slide. And for example, you can see from the drawing that we have a separation right here. So we define the entanglement entropy of the subsystem A as the von Neumann entropy of the reduced density matrix, where the reduced density matrix is nothing more than the trace over the degrees of freedom of the complement of the total density matrix. Of course, we have a prescription to calculate holographically the entanglement entropy, and this was conjectured by Ryo and Takayanagi in terms of a dual geometric object in the bulk. Essentially, the formula is this one, and we are instructed to find a codimension 2 hypersurface in the bulk that is extremal and also that satisfies that it smoothly retracts to the region A. Then to compute the entanglement entropy, we have to take the one that has the smallest area. So as I said, the minimal surfaces that compute entanglement entropies are space-like geodesics. So it would be useful to see some of its properties, or at least to present some of them. Here we have two types of geodesics. Both types of geodesics stay in the same constant time slice. The first one is that is in the left-hand side is the simplest that you can find. Is just a diameter. And the second one is another type of geodesic that you can find in this case. As you can see, to specify a geodesic, you need only two numbers. You can use the angular location of the endpoints, or you can use the angular opening and the angular location of the center. Can you hear me? Yeah.
Yes, we can hear you.
Okay. In the case where we have geodesics with time dependence, like this one over here, we can characterize the geodesic by four numbers. We can use the two previous parameters, alpha and theta sub c, but we can also add two additional numbers, that is the angle, the time opening, and the time location of the center. At this point, I think it would be useful to introduce another concept that it's called the kinematic space. The kinematic space in this context is nothing more than the space of all space-like geodesics. In the case where we have these geodesics that depend on time, kinematic space is going to be four-dimensional. But in the previous case, where we have geodesics that stays in a constant time slice, kinematic space is going to be two-dimensional. Let me now introduce the concept of differential entropy. So if we have a continuous family of oriented intervals, like this one, of course in the CFT side, then we define the differential entropy with this formula. And as you can see, it's like a very complicated expression, but we can get some intuition if we go to the discrete form of this formula. And we can see that this is nothing more than a sum and a difference of entanglement entropy related to this continuous family of intervals. What it was found by these people is that essentially the entanglement entropy is computing the length of a curve described by this geodesic, this family of geodesic related to these intervals in the bulk. So essentially what this formula is doing is taking pieces of these geodesics in order to reconstruct this curve in the bulk. But we can go one step further and we can relate the differential entropy formula with the concept of kinematic space. To do that, we just simply take the expression and we can always add a term that after integration gives you 0. This term is going to be the differential entropy formula of a point. and it gives you 0 because the length of a point is 0. So once we have introduced this term, we are allowed to introduce another integral, and we end up with this expression.
Sorry, Yaithd, I think Andres Sanabalen has a question. Andres, go ahead.
Okay. Okay.
Hello. Look, what is the so for the definition that you give? So you associate some entropy to a certain interval of a certain region of the spacetime, right? So
we are yeah.
And this like and you mentioned that this is related with a system that you can where the Hilbert space can be written as a tensor product, right? So my question is that, like for instance, imagine that you have like a very simple system, like I don't know, 2 photons that are entangled.
Okay.
So how this entanglement entropy reproduce this this entropy of a 2 photon system or something like this. So or how this the physics of entanglement is related with the intervals in space.
Are you referring to when I said differential entropy, or you're referring only just to the entanglement?
I'm referring already like it would be good to have like a simple example at the level of entanglement entropy, because you also associate.
I can elaborate more on this definition. For example, let me just say for now that the name of differential entropy is just given by the fact that you are using a difference between entanglement entropies. At this level, this is just a name that you adopt because of the formula. But specifically, if you want to talk about entanglement, what we are using here is that we are calculating the entanglement related, for example, to this specific interval. So these are two.
The question is that typically you associate the entropy with a physical system that is composed by objects. But like, so how is this relation of this association of entropy to a physical system to associate entropy to a region in the spacetime?
Okay, we can always use the concept of entropy whenever we have ignorance about our system. And for example, in the case of entanglement entropy, because of the reduction over the degrees of freedom of A, we don't know the specific total state. So in that case, we end up with a reduced density matrix, and we can apply, as we know, the concept of entropy.
Yeah, but the concept of entropy of is more related with the phase space, you know, not with the.
Yeah. But I would like to refer here to the concept of entropy as ignorance about our system. In this case, our system is A.
Okay, maybe for the sake of time, we can leave the discussion for later, Andres, if that's okay, or do you want to?
Yes, that's okay. Thank you.
Okay, go ahead.
Thank you for your question. Thank you for your question. So we end up with this formula right here. And what we have here, let me just put a figure in the next slides. We would like to interpret this formula. And what this is telling us is that we are integrating over a volume in kinematic space. Why kinematic space? Because given specific values of U and B, we can specify only one geodesic. So in this case, we are integrating over this kinematic space. Then the instruction of the integral tells us that we have to consider the geodesics starting from the tangent one to this one, and we have to take into account all the possible values of U. So in that way, what this formula is telling us is that if you want to compute the length of this curve, then you have to consider or to sum all the geodesics that intersect this curve. And you have to weight it with the double derivative of the entanglement entropy. So in that way, we can rewrite this formula in the following form. This is what it's called a Crofton formula. And it has two very important elements. The first one is the Crofton form. And as you can see, is nothing more than the double derivative of the entanglement entropy. And the second object that we have here is the intersection number, and gives you the number of intersections that the geodesic has with the curve sigma. And as I already said, the region of integration in kinematic space is going to be codimension 0. And for the specific case of the circle, the region of integration in kinematic space is this one. So one interesting consequence of this connection is that we can find the information of a point in the bulk in kinematic space. And the way to do that is by considering a closed curve that we can shrink to a 0 size. So in that way, we can prove that a point in kinematic space is going to look like a curve. We're going to call this object a point curve. And every point on this curve is going to represent a geodesic that passes through that point. In the specific case of ADS3, in a constant time slice, you can obtain the specific function for this curve, and is this one right here. We can also calculate the geodesic distance between 2 points, and the instruction is first to find the point curves related to this point and to this point, and then we have to integrate over the region inside these two curves, weighted by the Crofton formula, and in that way we can obtain the geodesic distance. But we can also obtain a prescription for the volume. In that case, we only need to integrate over the geodesic segment that keeps inside the region Q, and we have to weight this function with the Crofton formula. So there are a lot of things that we can calculate using the Crofton formula and the connection of kinematic space with the geometry of the bulk. So you can ask, what's the interpretation of the Crofton form? And in order to answer to this question, we have to use the strong sub-additivity inequality. Is this one right here. And we can consider a set of intervals that are very close to each other, defined by this figure right here. And if we put back the intervals in the strong sub-additivity inequality, we obtain that the left-hand side is nothing more than a discrete version of the double derivative of the entanglement entropy. And from the inequality, we can conclude that this quantity is greater than 0. By construction, we're assuming that du and dv are greater than 0. So what we have proved is that essentially the double derivative of the entanglement entropy is always greater than 0. So we can say that the Crofton form effectively measures the density of geodesics. Another important fact that unfortunately I won't be addressing this talk is that we can give a causal structure to the kinematic space if we take the following line element like this one right here. So this is all that we have to say for the static case. We discovered that the formalism of integral geometry can give us a nice interpretation of the entanglement structure of the vacuum of any other state of the CFT. Of course, the next step is to include time. And the first approach that we would like to consider is spacelike curves that have non-trivial time dependency. But the problem now is that the geometric interpretation is not clear. And it's not clear because when time is present, we have to consider a new degree of freedom that is redundant. It's like a gauge degree of freedom. So to explain that, I'm going to say a little bit more about a new concept. So what we also have learned is that the information of a closed curve is encoded in a family of intervals. But you can ask if this family is unique. And the answer is that it is not unique. We can consider another family of intervals that also contain the same information. And I have to define a generalized notion of tangency. we are going to say that a geodesic in the bulk, gamma, is null vector aligned with respect a given curve if it satisfies the following. First, it touches the curve for specific values of the parametrization. And second one, the tangent vector of the geodesic is equal to the tangent vector of the curve plus a null vector that is also orthogonal to the tangent vector. So to clarify this, let me just describe this drawing. We have the bulk curve, we have the tangent vector, we have the tangent, the null directions that are orthogonal to this tangent vector. So we are going to say, for example, that gamma is null vector aligned with respect to this point if gamma has as its tangent vector this purple one. So why this is a problem? So as I already explained, family of intervals that correctly computes the length of this curve is, for example, this one. We can consider the first geodesic and its ending point, a second geodesic and its ending point. And as we move around, we will see that the path that is traced by these endpoints stays inside this constant time slice. But we can use the null vector aligned condition or the generalized tangency condition to find another family of intervals. And this family, for example, I'm going to choose that the first one stays the same, but the second one is one that is null vector aligned. And the endpoint of this geodesic is this one. And as I move around, I can see that the path that is traced by the endpoint of the geodesic is going to be very different from the first one. So I can move on and calculate the differential entropy formula, for example, for the first family, and it's going to give me some result. And I can calculate the differential entropy formula for the second family at what I'm going to obtain at the end, and it's a general result, is that both families compute exactly the same quantity. So we can see from this figure that the information about the length of this curve can be contained in an infinite family of geodesics, infinite family of geodesics. So we can proceed as in the static case and use Stokes' theorem to obtain the Crofton form. First, we need the path on the boundary traced by the geodesic, the endpoints of the geodesics. I mean this x, l, and x right. And starting from the differential entropy formula, I'm going to integrate over some region that at the end is going to be the boundary of some other region. So if I use the Stokes theorem, I will end up with this expression right here. So there is no problem with obtaining the Crofton form, but the problem is that we don't have a geometrical interpretation. And the reason for that is that because of the null vector aligned condition, I could have started with this family of geodesics, or this family of geodesics, or this family of geodesics. And after applying Stokes' theorems, I would end up with a different region of integration in kinematic space. So consequently, I obtain an infinite number of Crofton formulas, and there is an ambiguity in the region of in kinematic spacing over which I have to integrate. To resolve this problem, we have to notice the following. In the case of ADS3, we have that all the null vector aligned geodesics with respect, for example, to this point, expand a null plane, a new geometric object that is common to all these geodesics. And this object is what we call a null plane. And the reason that we call this a null plane is because it satisfies these properties in unbending coordinates, essentially it's a plane. And important thing to say here is that the coordinates of the top have defined a two-dimensional region of integration in kinematic space. And this is exactly the kind of region that we would like to integrate to. So with this in mind, we can make a parametrization of the endpoints of any NBA geodesic. And instead of using the ending points of geodesic, we can use the location of the top point of this null plane to consider all the redundancy of the previous problem. And the specific parametrization that we use is this one, where U and B measure how close we are from XL and X right, how close we are from the top, I mean. And once we use this transformation, we end up with a Crofton form that gives you a specific region of integration. You have to integrate over the set of null planes that intersect to your given curve, and the expression is given by this. So a geometrical picture of this procedure is the following. We are using, instead of geodesics that intersect your given curve, we are using null planes that intersect. And the region in kinematic space is this blue region right here. Of course, you can use this prescription to calculate the length of curves that are a little bit more complicated, essentially the ones that explicitly have time dependency. And for very simple cases, you can find that this prescription works. So let me conclude with future work and conclusions. So we found that the generalization of the Crofton formula involves the intersection of null planes with a given bulk curve. The null planes contain all the redundancy associated with the NBA condition. And it would be interesting to generalize the previous kinematic formulas to calculate distance, volume, and other geometric measures in the time-dependent case. A nice question would be how to deal with regions in the bulk where the RT and HRT surfaces cannot penetrate. And it would be interesting to extend these formulas to other asymptotically ADS-tree spacetime. And why not to find a higher dimensional generalization using previous work by Balasonoman and Ravidio. And that's all. Thank you for your attention.
Okay, thank you very much. It was a very interesting talk. Do we have any questions? I